One important concept when we're talking about the electromagnetic waves are the concepts of energy and power. At the end, we know that an electromagnetic wave will apply a force to a moving charge given by the Lorentz equation, and of course that force exerted into a charge can result in work. So at the end, when we have an electromagnetic wave, what we have is a wave to transfer that capacity to do work from one place to another. So at the end, we have a way to transfer energy or capacity to do work from one place to the other. Now, what is that energy flow associated with a traveling electromagnetic wave? Well, this is given by what is known as the Poynting vector. Now, the Poynting vector, and its units are watts per square meter, the Poynting vector at any point of space just gives us the power density, and since it has these vector characteristics, what it's doing is it's telling us the direction of energy flow. The Poynting vector is computed as the vector product of the electric times the electric field times the magnetic field. Now, the flow of the Poynting vector through a surface, we can see that that is the rate of change of energy inside that volume. So what we're stating is that we have a certain volume defined by a surface S, and we compute this flow of the Poynting vector through that surface. This is the rate of change of the energy inside that volume. To see that, we're going to do some very mathematical derivations in which we're starting, well, which is the equation we just had seen. Now, we apply divergence theorem, and knowing just the definition, we have the Poynting vector, we can write something like this. Now, it's a lengthy development, but if we consider Faraday's and Ampere's law, we can see that divergence of this dot product can be written in this way, where actually we're using this notation. H squared is the dot product of H, and E squared is the dot product of E. So we can write this equation, and we make the following definitions. We define the stored magnetic energy inside the volume, given by this equation, the stored electric energy inside the volume, and that last term here is the power added through a generator or lost through losses. So, for instance, in the case in which we have a conductor with ohmic losses, we know that the current density is sigma, which is the conductivity times the electric field. So the lost power can be written in this way, and we can see that that rate of change of energy, which is just the power flow of the Poynting vector, is just the change in magnetic energy, the change in electric energy, and the power loss through ohmic losses. So we can see actually that the meaning of this Poynting vector is actually related, or it's actually giving us that rate of change of the power of the energy inside the volume. Now, for the one-dimensional case, the one that we have been studying in more detail, and remembering that electric and magnetic field are related by this we have that the Poynting vector has this expression, and we can see that the direction of the Poynting vector is Z, which is telling that the energy or the power flow is actually in that Z direction. We can also see that for this TM case, if we compute the stored electric energy and the stored magnetic energy, and given the relationship that there is between electric and magnetic field, we can see that those two energies are the same. So the stored electric and magnetic energy is the same for any given volume. That's not a general case, but it is the case for these TM electromagnetic waves.